Hi and welcome to the 20-minute presentation for our APROC submission on complete linkage in general metric spaces. This was a joint effort by Arutyunova, Großwendt, Heiko Röglin, Melanie Schmidt, and myself. And so to start off, let's in very broad strokes establish a setting or a context in which to situate the paper and in particular complete linkage. So we start with a very standard clustering problem, or two very standard clustering problems. So let's say we're given a finite set of objects and some dissimilarities between those objects in the form of a metric and an integer k. Now the goal is to find a k clustering of x, that is a partitioning of x into k disjoint sets C1 up to Ck, such that the maximum size of any of the clusters is minimized. Right, so this is the objective here, to minimize the maximum size of any of the clusters. Think of it like this: so dissimilar objects should lie in different clusters. Yeah. So there are two standard measures for the size. One is the diameter here on the left side, which is the maximum distance between any two points in the cluster, and one is the radius on the right side, which is basically the minimal radius induced by any point in the cluster. The left measure gives us the k diameter problem, and the right measure gives us the k center problem, both of which are well studied and well studied problems, very well known problems. Now, however, if we want to solve a real world clustering problem, it's not a priori clear what a good value for k is. It's quite unfortunate that this k is part of the input. So what do we do about that? Well, one approach would be to just solve the k center or the k diameter problem for all values of k, right? So we compute a sequence of clustering C1 up to Cn of x, such that Ci is an I clustering, and then we extract one or several clusterings of this sequence. Yeah. So, but the problem is when we do this is that it's very difficult to choose from these from the sequence, because the clusterings can be wildly different. So for any value of k, the k clustering and the k plus 1 clustering can be very different. They can, like, the structure can be very different. Yeah. So one way to what we do is to make them more comparable. We impose an additional structure constraint. So this is a kind of nesting condition. We additionally require that Ci should arise from merging two clusters of Ci plus 1, or conversely, Ci plus 1 should arise by splitting up a cluster from Ci. So in a way, this in the sequence from C1 up to Cn, this is a continuous refinement of a clustering of x. Yeah. So in a way, we can zoom in and out of clusters. So we can zoom into this cluster in Ci and get these two clusters in Ci plus 1, etc. So we clustered the space on different levels of detail in a way. Now, how do we evaluate such a sequence? Right, we do that on the basis of the flat clusterings, because we want to extract them at the end. So what we want is that the size of the I clustering is good relative to the size of an optimal I clustering, which does not have to satisfy any nesting condition. Yeah. So this is a definition of hierarchical clustering, which has an emphasis on this sequence of flat clusterings. There are other ways to define it, mostly in terms of this nesting condition, where the flat clusterings, the sequence of clusterings is more in the background or not even present. But the way we look at it is just how I define it right here. So how to solve this problem? Well, this nesting condition already gives us an approach, basically, right? So a bottom-up approach, where we start with a clustering consisting only of singletons, that would be Cn, then we successively merge pairs of clusters until only one cluster is left, one cluster is left. Yeah. This would be C1. Now, there are very many famous examples of such bottom-up approach. There's single linkage, there's complete linkage, there's average linkage, there's Wurtz method, and so on. All of these are also relatively popular. They are all implemented, for example, in the sklearn Python library. And so what we want to do is we want to understand how good the flight clusterings are that are produced by these methods, or in particular that are produced by complete linkage. So what does complete linkage do? Basically, all these approaches just differ in which pairs of clusters they choose to merge. And complete linkage is just a greedy approach. We merge exactly that pair of clusters where the diameter or the radius, so the size of the resulting cluster, is minimal. So just as in this picture, you can see the clusters that will merge at each step are those that have a minimum diameter. So we minimize the maximum distance between any 2 points in those two clusters. And so we do that until there's only one cluster left. So another question is, as I just said, and this is the main question of the paper, how good are the flight clusterings produced by complete linkage? Or more precisely, how good is the cost of the K clustering relative to the cost of an optimal K clustering? CK is the K clustering produced by complete linkage. And so for any value of K, really, for all values of K, this should be good. So let's talk about approximation bounds. So how good is the K clustering produced by complete linkage relative to an optimal K clustering? Well, previously, not really too much was known about this. So there's lower bounds for both the radius and the diameter, which are both like omega of log K. This is a result by Dasgupta and Long, where they've shown that for every K, there exists an instance where the K clustering computed by complete linkage is off by a factor of log K than that of an optimal K clustering. At the same time, really no non-trivial upper bounds are known. So what we do is we improve in both of these rows. So what we increase the lower bound, both in the case of the radius and the diameter, from omega of log K to omega of K. And we introduce upper bounds, O of K for the radius and O of K squared for the diameter. So for the radius, we show that this analysis is asymptotically tight, and for the diameter, it's almost tight. So the diameter is actually much more difficult to analyze. It has a different structure, and this is also the most difficult part of the paper, I would say. But the lower bounds are actually more interesting, and I want to talk about in this presentation. I want to talk about the lower bound for the diameter. So I think they're more surprising because this shows really that the clusterings can become quite bad. And also, what we show in the paper is that single linkage, which is really known to exhibit some bad behavior with regard to chaining, actually produces O of K solutions for both the radius and the diameter. So in some sense, complete linkage is just as bad as a single linkage when it comes to this. Although complete linkage takes much longer to build up these big clusters. Now, okay, so let's talk about the lower bound for the diameter. First, let's revisit the example given by Dasgupta and Long in 2005. What they showed is that for every K, there exists an instance xk, this K, such that the diameter of the K clustering computed by complete linkage is worse by a factor of log K than the diameter of an optimal flat K clustering. So let's look at the example, because we will kind of like improve this example. We will change it quite drastically, but it's a good starting point. So here's the example for K equal to 8. And what they do is they place 8 times 8 or 64 points on a grid in this fashion. And then they introduced the following distance. On the x-axis, that is on the horizontal axis, is just the discrete metric. So the value is 1 if the x-coordinates are different, and the value is 0 if they are the same. On the y-axis, on the vertical axis, they introduce a logarithmic distance, and the overall distance is just the sum of those. So why exactly this metric will become clear when we talk about how complete linkage approaches this instance. So first of all, let's check out the optimal K clustering for this solution, this instance, the optimal 8 clustering. So the optimal 8 clustering just consists of the rows, right? They have diameter 1, and just because we're dealing with the discrete metric, and so there is a solution of cost 1. However, complete linkage might produce a completely different solution. So we start with every point in a separate cluster, and now any merge that we could do will increase the cost by at least 1. This doesn't matter whether we merge horizontally or in some sense vertically. So what complete linkage might do is it might create these clusters. So instead of merging vertically, it merged, instead of merging horizontally, complete linkage merged vertically. So here we are in the same position again. So we could merge horizontally parallel clusters, but this would increase the cost by 1. So instead, we might just merge vertically neighboring clusters. This also just increases the cost by 1. And then we do that until complete linkage has fully reconstructed the columns instead of the rows. And on the columns, the distance was the logarithmic distance. And so instead of a solution with cost 1, we get a solution of cost log k. Now, let's quickly go over what happened. So successive horizontal merges incur cost of 1 only once. If we merge 2 clusters in the same row, then all of the other clusters in that row can be merged into that main cluster without incurring any cost. The diameter does not change because it's just a discrete metric. However, if we merge vertically neighboring clusters, then every time a cost of 1 is incurred. So successive vertical merges incur a cost of 1 every time. This is what we saw in the example just now. Now, successive vertical merges double the number of intersected rows. And so, well, we can only merge vertically log k times. And so every time we get an additional cost of 1. And so the overall solution is cost log k. Now, the logarithmic scale on the y-axis actually comes from this doubling of the number of intersected rows for vertical merges. The cost always has to be tied or has to be cheaper than horizontal merges. And so even though the number of intersected rows doubles, the cost can only increase by 1. That's where the logarithm comes from. And we cannot really increase the vertical distances because then complete linkage would just merge horizontally. So what we do in our example, we basically improve upon this third point. We kind of construct an instance where these merges do not double the number of intersected rows. Okay, so the idea is to merge diagonally, not quite horizontally and not quite vertically. So diagonal merges should incur an additional cost of at most 1 to tie them with horizontal merges, but they should not pay for other horizontal merges. They should not pay for other classes parallel to the one we just created. And they should increase the number of covered rows only by 1 instead of doubling them. So this way we can increase the cost by 1k times and so build up a solution of cost k. So let's see how we go about this. Well, we kind of keep the rows the same. We populate them differently. So the number of points on a row are different. But the main point is that we change the distance between the rows. So the instance is constructed of these basic building blocks that I just showed. These are what we call K graphs. So there's the 2 graph, which has 2 rows, and on every row is placed 1 point. So we have 2 points, and the distance between these points is 1. Now from this 2 graph, we construct a 3 graph by diagonal. So by having 2 copies, and 1 copy is diagonally shifted. Yeah. So like this, so that we get a graph like this with 3 rows now instead of 2. And then we add an additional edge from the lowest point to the highest point of weight 2. Now from the 3 graph to the 4 graph, we do the same thing. We take 2 copies of the 3 graph. 1 we shift diagonally, so we increase we increase the rows by 1 in a sense, so we get 4 rows. And then again we connect the lowest and the highest point by an edge of weight 3. So in general, the K graph is just 2 copies of the K minus 1 graph. One is shifted up the ranks by 1, the rows by 1, and then we add an edge of weight K minus 1 between the lowest and the highest point. Now what's important and what you can kind of see here, and it's a bit longer proof, but what you can kind of guess is that the diameter of the K graph is exactly K minus 1. So it's exactly the distance between the lowest and the highest point. That's what we have this big edge for, this edge of weight K minus 1. But you can also not get there any faster, because an edge of weight W connects rows that are spaced exactly W apart. So what we get is that the diameter of the K graph is exactly K minus 1 for K. And now, how does this help us? So let's see how we put these graphs together. So let's check out the example, the worst case example for K equal to 4. So there is an optimal solution here of cost 1. Again, we just pick the rows. They have diameter 1 because we're just dealing with a discrete metric. Now what complete linkage may do is something different. So again, we start with every point in a separate cluster. And now any new merge would increase the cost by 1, so we might just as well reconstruct the 2 graphs. They have diameter 1. Any new merge at this point again increases the cost at least by 1. So we might just merge the 2 graphs into the corresponding 3 graphs like this. They have diameter 2. And we continue like this until we have the 4 graphs reconstructed. At this point we have 5 clusters. Now there will be one last merge left where we merge 2 parallel clusters, and this increases the cost to 4. So here this solution constructed by complete linkage has cost 4, whereas the optimal solution has cost 1. Obviously this can be done for any K. We just take K plus 1 copies of the K graph and we place them next to each other like this, and then complete linkage may do the same thing. So that we get this theorem where for every K there exists an instance xk where the diameter of the K clustering produced by complete linkage is off by a factor of K than the diameter of an optimum flat K clustering. The same instance also works for the radius, for the lower bound for the radius, but you can check that out in the paper. And yeah, that was it. Like for all the other results, please check out the paper. And apart from that, thank you for your attention and have a nice day.